Okay, welcome back everybody. We're moving on to section 3.2. It's called Hamiltonian systems. And really, we're almost taking a step back because these are actually systems of ODEs and not systems of PDEs. So earlier we saw PDEs with a couple nice examples of characteristic curve solving flow PDEs. We're actually jumping to the side. Hamiltonian systems really are a topic of physics, and maybe some of your physics courses have covered these, but I don't necessarily think so. This is kind of an obscure topic in a lot of undergraduate educations, and I think this is a good excuse to cover this obscure topic. So what is a Hamiltonian system? I'm just going to scroll back up to this previous proposition that I'm going to remind everyone says we can find paths through level sets with a specific ODE. And that's going to be what Hamiltonian systems are as well, but in particular, we're going to care a lot about these level sets. We're going to construct the function f out of physics, out of a physical intuition for a system, and then that'll give us the ODEs that we're going to try to solve. So thinking about physics really quick, we're going to think about the conservation of energy in physics. And we're going to remark that just because energy remains constant, it doesn't mean objects aren't in motion. So in fact, a lot of physical systems, without any input of energy at all, or loss of energy, remain in motion. A couple of these examples are orbits. And by orbits, I mean quite a few different kinds of orbits, so celestial orbits, electronic orbits in atoms. We can talk about pendulums. Those are allowed to remain in motion, simple harmonic motion. It's like a weight attached to a spring that we've already talked about in this course. All of these systems don't need any input of energy, and as long as they start in a non-equilibrium position, then they're going to oscillate over time, or they're going to perform some sort of a motion that keeps their energy constant. And so what happens is within these motions, potential energy and kinetic energy oscillate, and they oscillate against one another, right? You have high potential energy at one point in time and very low kinetic energy at one point in time, and then at a later point in time they flip. So they kind of oscillate between potential and kinetic energy, and these are going to be what's called the Hamiltonian orbits. So what do we want to think when we're talking about Hamiltonians and their orbits is we're going to define a function h, which is non-negative, and it's going to be a function of q and actually q prime. So it's a function of position and the time derivative of position, also known as velocity, or momentum, because mathematicians like to set mass equal to 1, and so velocity and momentum are the same. We actually use the variables q and p rather than q and q prime, and our function h maps between q and q prime, or q and p, and it outputs a positive real number. We're going to call that the energy, or the Hamiltonian. Okay, so we just have some system that's a function of two sets of d-dimensional variables, and it gives me a positive number. That's my energy. I'm just going to call that the energy of the system. Depending on the system, the interpretation of q and p may be different, but we want to just call that the energy of the system, or the Hamiltonian of the system. We then define this system of ODEs is defined from h by gradients. Okay, so it's defined from h by the following gradients. What do these mean? What does this gradient with a subscript mean? Where gradient sub p is the vector partial p1, partial p2, partial pd, and gradient q as a vector is the gradient of vectors only in q. So q1, q2, qd. Right, and I think that's a fairly natural interpretation of that subscript on the gradient. We're just saying, like, arguably the true gradient of h should contain all of q and all of p. So what we're doing is restricting the gradient to the p directions for the first case and the q directions for the second. So this is where you can see that interplay, right? We're basically saying that how does q evolve over time? Well, it evolves in the gradient of p of this function h. How does p evolve over time? Well, it evolves in the negative q gradient of h. And that's just called a Hamiltonian system. We're just going to take it for granted for what it is right now as a definition. And we're going to see really what's going on with this corollary. What is this a corollary of? Keep in mind the word corollary means it almost follows exactly from an earlier proposition or theorem. That corollary is actually a corollary of this proposition in the previous section. So that's why I started this section up there and said we're occupying energy levels. Conservation of energy means that the energy does not change over time, aka we exist in the level set. We always exist in the same energy level, also known as level set, right? So an energy level of H is the same thing as a level set of H over time. So that's why we are a corollary of that previous proposition, this corollary at least. It says, hey, suppose that we actually set up our Hamiltonian system. There's the system along with an initial condition, Q0, P0, and you define your initial energy as just the value of H on Q0, P0. Then in fact, the solutions, Q prime, P prime, will allow you to always exist at the same energy. So in some sense, we're using physical intuition to describe trajectories, because what's the point? We want to find trajectory of particle or whatever we're working with, but let's just call it a particle Q, right? So if Q represents the position of a particle at some point in time, we really want to find its trajectory. How can we actually construct a system which will predict this for us? We can construct it by defining energy and then forcing it to remain constant. And this is the process by which we can force the energy to remain constant and still allow my function to evolve, my position to evolve. So energy remains constant, and yet I still have some motion, some non-trivial motion. This is the point of Hamiltonian mechanics. So I've got a proof there. It really is a corollary. The proof is the exact same as the previous proposition, with the one special caveat that this is technically the ODE you would find. All right, so that's the ODE that you find if you follow the proposition. But what can we do with this ODE is we can split it. These dot products, we can split it and we can compare terms against each other, since to a certain extent we have the ability to find Q prime and P prime. So we compare the terms of Q prime and P prime against one another, and we see that exactly what they need to be equal to is each other's gradients with a negative sign on the P term. So I've got this remark that says that these are special characteristic curves. Certainly that has to be the case, right? Because basically what we're doing is we're solving this equation, Q of T, P of T equals 0. What is a solution, right? This equation is by definition conservation of energy. So we're just solving the conservation of energy equation. And what is a solution to the conservation of energy equation? Well, it's a characteristic curve of our particle's trajectory. So that's how we can think about these as characteristic curves. And then the rest of today's section, I'm just going to be covering 3 nice examples. So let's start with the pendulum. This is a very classical example of a Hamiltonian system. I'm going to take a weight and I'm going to pull it away from equilibrium by some amount theta, some angle theta. Let's make it a bowling ball. So I've got a bowling ball that's been shifted away from equilibrium by theta. And I'm going to ask the question, I want the energy of ball. What is the energy of this bowling ball? Well, it's going to have a potential energy. You might say the potential energy is mgh, but what is h? What is h? Well, by similar triangles, there's a theta. What is m? It's going to be cosine. Or so it was h, it's going to be cosine theta. Or it's really 1 minus cosine theta. And then there's technically an m times g here, but I'm pretending that those numbers are equal to 1 because I am a mathematician. So the height that I'm away from equilibrium is 1 minus cosine theta. And we're going to talk about its kinetic energy. Its kinetic energy is not changed at all. It's got some angular velocity, so that's going to be theta prime. And we're going to do velocity squared over 2. Recall that the mass we can make to be 1. The gravity we can make to be 1. So mv squared over 2 is just going to be theta prime squared over 2. So you can calculate potential energy. You calculate a kinetic energy. What do you suppose the Hamiltonian is? Well, it's the sum of potential energy and kinetic energy. So we're just going to sum those together directly. And now we have to be a little bit clever. The Hamiltonian is supposed to be a function of space and velocity. So velocity here is theta prime. So everywhere I see theta prime, I'm putting a p in there. Space here, or the potential energy is theta. Everywhere I see theta, I'm going to put a q. So our Hamiltonian for the pendulum is 1 minus cosine of q plus p squared over 2. This allows me to construct the Hamiltonian system. So once I have this, I can construct a system just following its definition. Q prime is always the gradient in p. This is a one-dimensional problem. What's the gradient in p here? It's just the partial derivative in p. Partial derivative in p, you'll notice, is just p. P prime needs to be the partial derivative in q, or the gradient in q, same thing. The 1's gone, the p squared over 2's gone. I get negative sine of q. This should probably be a positive. It should be a positive sine of q there. Sorry, but it's the negative sine of q. So I do have a negative sine of q. All right, so that's p prime. And then, so this is just a system of two ODEs. Unfortunately, however, it is a nonlinear system of these two ODEs. So my life is not too easy, right? A system of nonlinear ODEs is kind of one of those things that we don't know how to solve that well. We could follow proposition 1.3.14. That's the one where you find some potential function, capital G, satisfying some necessary criteria. It's really hard to find that. So what we do instead, thankfully, that this is a one-dimensional problem, we can get away with a little bit of a cheat, which is that we know that Q and P, the trajectories Q and P, have to satisfy conservation of energy. And because we have two unknowns as well as one equation here, we can actually solve this equation for Q prime. What is Q prime in this equation? Never forget, Q prime and P are the same thing. So never forget that Q prime and P are the same thing. So we can solve this for Q prime and we get the following. So now this is a one-dimensional nonlinear ODE. This is really only a special case that we can do it when our original system was two-dimensional. If our original system was like 12-dimensional, then we're stuck. So since our original system was two-dimensional, we were able to solve it for just Q prime in terms of Q, which is a one-dimensional nonlinear ODE. In this case, it's separable. And so we can follow the corollary 1.3.16 to solve separability in defining capital psi as the antiderivative of 1 divided by the right-hand side and the variable q. And then the solution is psi inverse. This is an inverse function of t plus psi of our initial value, as well as p is obviously just going to be the first derivative of this solution. So we are able to solve for q and p here. Unfortunately, this is a non-elementary antiderivative. And so we don't really have a closed form solution to the pendulum problem, but we can numerically approximate this antiderivative, and it's not too hard to numerically approximate the antiderivative. We get the following evil eye looking phase plane analysis. So let's talk really quickly about what phase plane analysis is. This is a phase plane analysis of the solution in the sense that here's Q. This is like the axis, the Q axis. This is the P axis. Where is T on here? Because both Q and P are functions of T. So the question is, where is T? Where is T? T exists at all points in time. So you can think about me starting at like T equals 0 is this point. Maybe T equals 1 is here. Maybe T equals 2 is here. Maybe T equals 3 is here. And so on. And this is going to be true for every single curve on my phase plane analysis. We can think about this. This is actually what the system looks like over all time, and I'm tracing it out in both the Q direction and the P direction. So T evolves over time around these curves, and it's true for each curve. Each curve corresponds to a different initial condition. So each curve corresponds to a different set of initial conditions. And what is a different set of initial conditions when we're talking about conservation of energy, also known as a different energy level? So what do phase plane analyses actually do, or Hamiltonian orbits show, are different energy levels? So what we see here, these are all discrete. They don't intersect with each other. Each one is an energy level of the system. So the system's energy remains constant on each one of these. But you can think about over time, what happens is we travel around these, And it's only a one-dimensional system, right? The pendulum just looks like this, and it kind of swings to one side, and then it swings to another side, and then it swings to the other side. So we should only be thinking about space is just this q-axis. We're only thinking about spatially, we're moving like this. But what do these points describe? These points describe at the equilibrium in the bottom, equilibrium position, but with positive or negative momentum, right? Because the momentum of the ball when it's straight down is either going to be pointed to the left or the momentum's pointed to the right. So that's why we have these momentum directions there, up here and down there, that describe our momentum values. So that's what the phase plane analysis of Hamiltonian systems looks like. I have also only plotting the position coordinate over time, because I know a lot of you would complain if I didn't. And you can see if I start with a collection of 6 different initial conditions, they all kind of play different games as a pendulum. And you let those evolve over time, and that's what you get. So I have not plotted no plots of P here, which makes sense. I'm only trying to plot the position of this pendulum. But that's how the pendulum evolves over time. So that looks kind of nice. The next example is the harmonic oscillator with friction. And if we jump all the way back to example at the beginning of the book, we did talk about harmonic oscillators in the beginning of the book. And we talked about how they kind of take this form of x double prime plus gamma x prime plus kx equals 0. That was our harmonic oscillator in section 1, or the very first section in the book. And we're going to see if we can derive something similar to that using Hamiltonian dynamics. So what do we want to think about with a harmonic oscillator? Just at the same as the beginning, is you have some spring, and there's a mass at the end of the spring, mass m, and there's a spring constant k that allows the spring to oscillate around equilibrium, because it provides a restoring force away from equilibrium, and then maybe there's some friction of friction parameter gamma. So let's think about what the total energy may look like in this situation. Well, we still are going to have potential energy. What is the potential energy going to look like? It's going to be held in the spring itself. The potential energy of the spring is going to be proportional to distance squared from equilibrium. Now, why is this the case? We're thinking about energy can be thought about as work, and you'll recall that work is force times distance, and the force, the spring constant force, is kx. The position from equilibrium is x, so this should be kx squared, or at least proportional. I put it divided by 2 just to make my life easier on here. And it's actually because you're integrating this distance over itself. So this is really kx x dx, and this is why you get kx squared over 2. So the work done by the spring constant is going to be the potential energy of the spring constant. That's going to be kx squared over 2. We're also going to have kinetic energy proportional to the square of the current velocity. I don't think this surprises anybody. This is just mv squared over 2. And the velocity will just be x prime. And then we will actually have some energy loss due to friction, if we want to go back to section 1. And the friction is also going to be proportional to velocity multiplied by the position. So this is going to be akin, once again, to the force times the distance. Is going to be gamma x prime x. So those are going to be my 3 terms that are going to play roles into energy here. And so what is the total energy of the system H? Well, it's going to be the potential energy plus the kinetic energy. And then there's this extra term that people are going to think I'm crazy for including, E dis. So what have I actually done here is I'm going to artificially inflate the energy of the system by what it loses. Right, so if I know I'm losing energy, I'm losing gamma x prime x energy in my system. What I want for the Hamiltonian, because the Hamiltonian describes conservation. What I want from the Hamiltonian is I'm going to force conservation of energy by artificially inflating the energy of my system by the amount that it loses. So the Hamiltonian, we're going to include the energy that the system loses in the Hamiltonian, because I'm going to be constructing these Hamiltonian paths which need conservation. So if I have conservation of energy, what I lose from the system would normally disappear, but I'm going to pretend like it's always there. Even if it's not necessarily in the specific system itself, I'm going to say it's still around, it's somewhere. And so I'm adding that into the Hamiltonian anyway. And then I'm going to translate, okay, fine, the potential energy was kx squared over 2, the kinetic energy was x prime squared over 2, and the dissipation was gamma x prime x. And if I want to write this in terms of the position and the velocity, then I have q squared over 2, p squared over 2, and pq. From this, I can actually construct my Hamiltonian system. right? Because what do I have here? This is partial pH, this is partial QH. So if I decide to set this up as a system of two ODEs, linear system of two ODEs, then I can establish my matrix, which is just the coefficients, right? This is why we studied in chapter 1 how to recall all of this stuff. So the p variable is the second one, the coefficient is a 1, the coefficient on the q variable is negative k, and the coefficient on the p variable is minus gamma. There's my matrix. If I compute the matrix exponential of this, then I end up with exactly what I expect, the matrix exponential against the initial condition. If I plot these, we actually, in the phase plane analysis, once again, I've got some phase plane analysis. Plotting this in the phase plane, we see that over time, right? Over time, this is the idea we think about in the phase plane analysis, is each one of these points is a point in time. And what's happening in space is I'm actually oscillating in smaller and smaller spaces until friction kills me off, right? Until eventually friction is pulling me towards equilibrium in the center. So this is the phase plane analysis of the harmonic oscillator with friction that we can derive using Hamiltonian systems and Hamiltonian mechanics. And so you can immediately see when you have something like energy dissipation in phase plane analysis, or just with a Hamiltonian system in general, if you end up solving it. Our third case, now this one was nice. The second case was nice because we actually were able to solve this exactly using theorem 1.3.6. A lot of these Hamiltonian problems will be nonlinear, and they'll be nonlinear systems, so we can't always solve it. But this last example, I think, is a useful one to just refer to the fact that celestial orbits, in the sense of, you know, what we are as the Earth revolving around the sun, that is a Hamiltonian orbit. So we can set up celestial orbits as the following. Let's talk about our three-dimensional point in space. Vector x is the vector xyz, and we'll put the origin as the position of a star. So x will be the position of a planet, 0, 0, 0 will be the position of a star. It orbits. Let's talk about the potential and kinetic energy of a planet. Well, the potential energy of a planet is gravitational potential energy, mgh. And if we have mgh here, what is the height? The height away from the star in the center of the solar system. The height is just going to be the distance to the star. So height of planet to star is distance to star. So that's going to be the magnitude of x. And then I've got some, gravitational constant g there. And then what is the kinetic energy of this planet? Well, that's going to be the velocity squared over 2. So that's x vector prime magnitude squared over 2. Once again, I've set mass equal to 1. And so if we add these together, the potential and kinetic energy, if we add them together, we get g times the distance plus the kinetic energy. So we have g magnitude q plus p squared over 2. And this is in a higher dimensional system. Now I will actually have to consider the full gradient. If I take a gradient of h in the vector p, what's going on here? Well, the vector q doesn't care about the vector p at all, so that's gone. The gradient, let's think about what p squared, the magnitude of p squared over 2 actually is. Magnitude of p squared as a vector is p1 squared plus p2 squared plus p3 squared, all divided by 2. If I take the gradient of that, I get the partial derivative in p1 of h, the partial derivative in p2 of h, and the partial derivative in p3 of h. That's going to give me 2p1 divided by 2. So 2p1 divided by 2 is just p1, 2p2 divided by 2 is just p2, 2p3 divided by 2 is just p3. What do you know? This is exactly the vector p. Moreover, if I take a derivative in the variable q, or a gradient in the variable q of h, this is going to be q1, or partial q1, of what is the magnitude? The magnitude is the square root of q1 squared plus q2 squared plus q3 squared. So if I take a derivative of that in q1, what do I get? I get 1 divided by the square root q1 squared plus q2 squared plus q3 squared, and there's a 2 that comes down from the power rule, and then there's a chain rule that comes in and says, hey, take a derivative of that q squared, and I get 2q1 squared. So my 2's cancel, and I get q1 squared over the magnitude. If I replace this with an I, it'll just be any of the q's of q2 squared over the magnitude, q3 is q3 squared over the magnitude. And so the gradient of this, gradient in q of magnitude q, is going to be the vector q divided by its magnitude. And that's what we see here. So negative gradient in the variable q of h is exactly what we see there. So if I set up this system, This is actually a really, really tricky system to solve. There's not really a good way of solving this system at all. We could attempt to use proposition 1.3.14, but I find it very unlikely that it would work very easy for us, so we just have to solve this numerically. So jump back to Euler's method, Runge-Kutta methods, whatever you learned in ODEs, solve this one numerically. And I've done that as well, solved it numerically here for a vast number of initial conditions and plotted the orbits. So you can see there's this little tiny blue dot right in the middle, and that's our star in the middle, and all of these are orbiting the star. And so you can see that these have some very interesting orbits around the center there. I mean, if you were, this is why, we have a little bit of a precession in our orbits. Obviously, with finer tuned masses and gravitational constants, we would get closer and closer to what we actually experience as the Earth revolving around the sun. But this is just a nice example to see that you can definitely construct very traditional celestial orbits around something in the center just by setting up potential and kinetic energies. But anyway, that's all I've got for Hamiltonian systems. They're like a fun way to think about that physics can really give us trajectories just by thinking of conservation of energy and characteristics within energy levels. But anyway, that's all I've got. I will see you in class later. Bye.